What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 3, Section 5, Transformation of Functions. Let's do it. When examining the formula of a function that is the result of multiple transformations, how can you tell a horizontal shift from a vertical shift? So if I have a function, let's say f of x, if I'm looking for a horizontal shift, it's going to be applied directly to the input, either in addition or subtraction. For example, if I have x plus 2 like this is a horizontal shift left. I know it says plus, so you might think right, but it's actually the opposite for the horizontals. Horizontal left by 2. If I see f of x minus 2, that's horizontal right by 2. If I see the entire function f of x being added to 2, right, or 2 plus that function, now we're talking about a vertical transformation up 2. So it's interesting with the verticals, if it's plus, it's up, it's minus, it's down. That's a little bit more intuitive. Obviously, the horizontal, it's not like that. And then again, if I take that entire function value and I minus 2, this is again vertical down by 2, boom, done. When examining the formula of a function that is the result of multiple transformations, how can you tell a horizontal compression from a vertical compression? So let's first talk about a vertical compression. Let's say we have f of x being our function. If we're talking about a vertical compression, we're going to be multiplying this entire function by a value between 0 and 1. So for example, like 1/7. This would be a vertical compression, kind of smushing it down, making it look wider. Now, what about a horizontal compression? This is where we're smushing the function in. It kind of looks like a vertical stretch. So this is a little bit of a different scenario. Again, things that are referring to horizontal changes, they're going to be affecting the input. So what it would be is I'd be taking my input and I'd be multiplying it by a constant. Now the question is it a constant greater than 1 or a constant between 0 and 1? So for a horizontal compression, it's actually going to be a value greater than 1, like 2. If we had a horizontal stretch, conversely, it'd be a fraction like 1/2 in the mix there. So just to recap, vertical compression, horizontal compression, boom, done. How can you determine whether a function is odd or even from the formula? So there's a quick test that you can use to figure out if a function is even or odd. So in either case, you're going to start by plugging in negative x for the function. If what you get as a result is the original function itself, meaning there's no actual change, like you plug in a negative x and it just looks like the original function itself, this would be an even function. A great example of this would be x to the 4th plus 2x squared, right? If I plugged in a negative x here, it'd be negative x to the 4th, which is just positive x to the 4th. The negatives are going to cancel out. Same with the x squared. So this would be an even function, boom, done, and it would pass that test. Now, if we plugged in a negative x and instead the entire function was flipped, this would be an odd function. An example of this would be 3x to the 5th minus x cubed, right? Plugging in a negative x here, negative x to the 5th would be negative x to the 5th. So this would be negated, and this would be negative x cubed. So that would be flipped to a plus x cubed. So the entire function is therefore negated. It is odd. And last but not least, a quick example of a neither scenario, because it could be neither odd or even. You could have sort of like a little bit of a hybrid. You could have 3x squared plus x, right? If I plug in a negative x, this is going to stay the same, and this x is going to flip. So it's not fully staying the same, it's not fully flipping, therefore it's neither. So here we're taking our function and we're shifting it down 3 units and to the right by 1. Now I'm going to apply the horizontal or right shift first. So our function will now be x. And again, when we're going right, it's sort of the opposite of what you'd anticipate. You'd think plus would go to the right. In fact, it's minus 1, so that's right to the 1. And then down 3 units. Now, this is the more intuitive part. We're just literally subtracting 3. That moves us down 3. Boom, done. For this one, again, I'm going to look at the horizontal shift first, then the vertical shift to apply it to this function. So first, we're going to apply that left by 4 units. So again, it's something squared. So we want to apply it directly to the input, to the x value. So I'm going to add 4. And again, adding 4 is actually taking me to the left. So we got x plus 4 squared, and we still got 1 up here. And then it says shifted up by 2 units. So we're going to take the entire function as a whole, and we're going to add 2 to that. That's the vertical shift by 2. Boom, done. So here we're just identifying the transformation occurring. This is a horizontal shift because it's being added to the input. And which way, left or right? It's left because it's plus. So horizontal shift left by 43. For this function, since the change is occurring to the input, it's a horizontal shift, but what specifically? A horizontal shift to the right by 4. Again, when it's minus, we're actually going to the right. If it was plus, it'd be going to the left. For number 15, we're adding 8 to the entire function. That is a vertical shift, and this is a vertical shift up because it's a plus, going up by 8 units, boom, done. For number 17, this is a vertical shift because we're applying a constant to the entire function. Since it's minus, it's down, and it's a vertical shift down by 7, boom, done. So for this one, we got 2 transformations occurring. First, we got the inside. That is a horizontal shift. And since it's a plus 4, we're actually going to the left by 4. And then out here, we're applying it to the entire function. Therefore, it's a vertical shift. And because it's subtraction, we're talking about a vertical shift down by 1, boom, done. So for this question, we're meant to figure out where this function is decreasing and increasing. Now, this is something to the second power, hence it is a parabola, right? And we know since that a term, aka 5, is positive, we know it's going up. Now, what we really want to figure out is where is the vertex, because the vertex is the change from a negative slope to a positive slope, aka from decreasing to increasing. And here is vertex form, which means I know what the vertex is. It's at the opposite of this, which is -3, comma, whatever this value is, which is -2. And this is really helpful because now I know that the decreasing part occurs all the way from -infinity up to -3, up to the vertex. And then the increasing portion starts at -3 and carries on forever to infinity, boom, done. So first, let's understand what this function is. It's a square root function, and there's a couple transformations occurring. Number 1, there is a negative here. Number 2, we've got a constant out here that's going to be a vertical stretch. And last but not least, we have this vertical shift down by 1. So let's apply these. So first, our normal radical function would just look like this, okay? But it's negated and stretched. So the negation in the front is a flip across the x-axis. Then it's stretched out by that 3, and then we're shifting it down by 1. So this thing is coming down by 1 like so. And so this would be something like what our final function looked like. Now, this is helpful because we can see what the slope is, we can see the domain, all that good stuff. And it looks like the slope is always negative. It's never going to go positive. It's never going to come back up. That's not what a radical function or a square root function does, which means that this is always decreasing, and it's decreasing right from that starting point, right from that origination point, which is 0, -1. So it's decreasing from 0 all the way to infinity, boom, done. So this graph up here of f of x is 2 to the x, and we're trying to apply this transformation, aka taking 2 to the x and subtracting 3. So when we subtract from 3, it's a vertical shift down by 3 units. So to apply that here, I'd go 1, 2, 3, essentially for every point. Let's do another point right here, 1, 2, 3, and maybe this one here, 1, 2, 3. And therefore, our new sketch of the transformed function would look like this, approximately, of course. Boom, done. For this one, we want to start with our parent function, which is x squared, right? And that's just our normal function like so. And what we're doing is we're shifting it left by 1 and down by 3, right? That's a horizontal shift to the left and a vertical shift down. So the vertex is going to go left and then down by 3. And then literally the new function would be, the same sort of progression, just starting at a lower point. And this is the new function like so. Boom, done. So for this one, our parent function is x cubed, and that looks roughly like this. Now, when we apply the transformations, first I see 2 to the right, and then out here I see 1 down, right? It's a horizontal shift to the right, a vertical shift down by 1. So we go 2 to the right, down 1. And so that's our center point, right? We moved it here. Then these other points, now we go up 1 to the right, down 1 to the left. And even this point, we can shift 2 to the right, down 1, 2 to the right, down 1. And there's our new function, boom, done. So for g of x, writing it as a transformation of f of x, it looks like the exact same outputs, but everything For the x value has been shifted once to the right? Like where it was -2, now it's -1. Where it was 0, now it's 1. So we know a shift to the right is minusing 1 from the input, which means g of x is f of x minus 1, boom, done. Now when we look at h of x compared to f of x, it looks like all the outputs are being added by 1, right? -2 becomes -1, -1 becomes 0, etc. So h of x, therefore, is simply our entire f of x function, but we're adding 1 to the output, so there's your answer, boom, done. So for this one, we're meant to write an equation using transformations. Now, obviously, we're starting with an absolute value. We know that this is some sort of an absolute value function. Now, normally, your absolute value parent function is going to start here, and it's going to go up and to the left and to the right like that. But this is almost the exact same. It's just the vertex has been moved. It looks like 3 to the right and 2 down, which means a horizontal shift 3 to the right would be x minus 3, and a vertical shift down by 2 units would be minus 2 on the outside. So this is your final function, done. For this one, the parent function is, of course, the square root of x, and it's just been shifted down 1 and to the left by 3. So to go to the left by 3, we would add 3 to x, and then we go down 1, we'd subtract 1, boom, done. This one is, of course, a parabola, so we're starting with a parent function of x squared. All that's happened here is it's been shifted to the right by 2, so it's going to be x minus 2 squared. That's going to do a horizontal to the right by 2, boom, done. For this one, our baseline function is, of course, an absolute value function, and it looks like it's been shifted 3 to the left and 2 down, but everything else is the same. So our function would be absolute value of x. And again, shifting to the left, we're adding 3. And then shifting down by 2, we're subtracting 2 from the entire thing. Boom, done. So for this one, all we've done is we've taken our original square root function, which normally goes like this, and we flipped it or reflected it across the x-axis. So when we do that, we're applying a negative to the entire function, aka f of x equals negative rad x. Boom, done. So for this one, we've had 3 transformations, right? We've shifted it to the left by 1, we've shifted it up by 2, and then we reflected it, right? It was going up, now it's going down. So first I'm gonna apply that horizontal shift to the left. That's by adding 1 to the input. Then we're gonna reflect it down, right? We're flipping it down. That's gonna be the negation. So at this point, the vertex is here and it's going down. And then the last step is we have to shift it up by 2, shift that vertex up by 2. So we're going to add 2 to the entire function. Boom, done. So the parent function here, of course, is square root of x, right? Because it's that arm shooting off. But in this case, it looks like it's been shifted up and reflected across the y-axis. So to reflect across the y-axis, we represent this as negating the input. So negating the x on the inside. And then we're shifting it up by 1, boom, done. So here we're going to test if this is odd, even, or neither. So what we do is we plug in negative x. Now, what is negative x to the 4th power? That's simply x to the 4th, which means plugging in negative x just gives us our original function, which means that this is even, boom, done. So again, we're going to replace all the x's with negative x like so. And this gives us negative 1 over x minus 3x, meaning everything is flipped. The entire function has been negated, which makes this an odd function. Boom, done. For this one, if we replace x with negative x, and then we raise it to the 4th power, it becomes 2x to the 4th, which is the exact same as the original function. Hence, this is even. Boom, done. Now, for this one, when you attach a negative to the original function on the outside like this, this is a reflection across the x-axis. Boom, done. Now, whenever you have a constant in front of the function, we're talking about a vertical stretch or compression. Since this is greater than 1, it's a vertical stretch. So we say vertical stretch by a factor of 4, boom, done. When we have a constant on the inside multiplying the input, we're talking about a horizontal stretch or compression. In this case, it's greater than 1, so it is a horizontal compression. So we call this a horizontal compression by a factor of whatever is the reciprocal of that constant. So we say by a factor of 1/5, boom, done. Once again, we have a constant multiplying the input, which means it is a horizontal. And is it a stretch or compression? because it's between 0 and 1, we say a horizontal stretch by a factor of the reciprocal of that constant, which is 3, boom, done. So for this one, we have two transformations. First, the negation to the input, that is a reflection across the y-axis. And then the 3 on the outside is a vertical stretch or compression. Because it's greater than 1, it is a vertical stretch by a factor of 3, boom, done. So here we have two transformations. First, a reflection across the y-axis, and then a horizontal compression. So for a reflection across the y-axis, we want to negate that x value like so. But now, since we're talking about our compression horizontally, we need to also include a constant inside here. And since they said by a factor of 1/4, that means the reciprocal of that goes inside like so. And this makes a lot of sense because we know that horizontal compressions exist when that constant is greater than 1. Obviously, I'm talking about the absolute value, right? So this makes sense as the new g of x, boom, done. So here we've got a vertical compression by a factor of 1/3, shifted to the left by 2 and down by 3. So let's start with that shift to the left by 2. So we're going to take our x and we're going to add 2 to that, right? Because adding 2 to the input actually shifts it to the left by 2. Then we are going to vertically compress it by a factor of 1/3. So it's like multiplying this entire thing by 1/3, but 1/3 times this is basically multiplying the denominator by 3. So there is our vertical compression. Last but not least, we're shifting down by 3. So we take the entirety of this and we subtract 3, boom, done. So here we've got a vertical compression by a factor of 1/2, shifted to the right by 5 and up by 1. So we're going to start with that shift to the right by 5. So here we would say minus 5 because that actually shifts it to the right by 5. Then we're applying this vertical compression, which would be a 1/2 in front, and then shifting up by 1 unit, adding 1 at the end, boom, done. So if we take our original x squared as the main parent function here, what are we doing? We're shifting to the left by 1, that's this. Then we're vertically stretching by a factor of 4, that's this guy. And then we're shifting down by 5, that's this right here at the end. So first applying the shift to the left by 1 and down by 5, our new vertex is going to be here at -1, -5. And it's still going up, but now it's stretched by 4. So normally we'd go up by 1 here, now we're going to go up by 4, like so. To get one more point just for fun, I'm going to plug in 1 here. 1 plus 1 is 2, 2 squared is 4, times 4 is 16, minus 5 is 11. So that next point would be up here, and using our axis of symmetry, we also know it would be up here. You can test it by plugging in -3. That's a pretty good bet. And now we can try and graph this as best as possible. And that's what it looks like. Boom, done. So here we actually got 4 transformations occurring to the absolute value function, which is normally upwards v like this. First, we're going to the right by 4. Then we're vertically stretching by a factor of 2. Then we're reflecting, that's the negative, across the x-axis. And then last but not least, we're moving up by 3. So first thing is I'm going to look at my original vertex, which is at 0, 0, and we're shifting that 4 to the right, and then we're going 3 up. So here's my new vertex. Then we're flipping it down. That's a reflection across the x-axis. So instead of going up, now it's going down, and we're stretching it by 2. So instead of kind of going this way, we're now jumping by 2. It almost looks like a slope of 2 like so. And again, if you're not sure, you can plug in points, right? If I plug in 6, I get 6 minus 4 is 2, times -2 is -4, plus 3 is -1. Check it out, 6, -1. It works. So here's the function. And by the way, when I did that flip at the end, I just flipped it down, right? So you might be like, well, wait a minute. I thought you said it was a reflection across the x-axis. So notice, in reality, the actual order in which you would apply these changes is right. We're doing that shift to the right, and then I'm flipping it down after that shift to the right. So it'd already be going down at this point. Then we stretch it, and then we move it up. So that's why it's still going to look like this with a nice vertex of +4, +3, boom, done. So for this one, we just have one transformation, which is a vertical compression by 1/2. So everything is still going to start here at 0, 0. Now, normally I'd plug in 1 and I'd get 1, but here it's vertically compressed by 1/2. So instead of getting 1, I'd get 1/2. And you can verify this by plugging in 1 and plugging in -1. You'll see you'll get a half and -1/2. Likewise, normally I'd plug in 2 and I'd get 8, but here we're getting half of that, which is 4. So 2 would be 4. -2 would be -4. So this gives you a rough idea of what this would look like. It would look like this. Boom, done. So in this function, we have two transformations happening. First, a constant applied inside. So that is a horizontal stretch by a factor of 3, right? It's a reciprocal of that. And again, 1/3 between 0 and 1, absolute value wise, is going to be a stretch. And if it was greater than 1, like 2, 3, or 4, that'd be a horizontal compression. And then we have that -3, which is a vertical shift down by 3. So applying this first, normally our center would be at 0, 0 for a cubic function. Now it's going to be at 0, -3. And again, we're stretching it horizontally, right? So it's stretched out. So where I'd normally have 1 would be here. Now we're stretching it horizontally by 3. Boom, boom. So this point would now be moved out here. It'd be tripled. Likewise, the point here, which would normally be here to the left, is now tripled. Boom, boom. And it's out here. Now, just to get one more point, just for fun, I'm trying to pick easy points that are easy to plug in. I'm going to plug in 6. So 6 times 1/3 is 2. 2 cubed is 8. Minus 3 is 5. So 6, 5. And same deal, -6. So -6 times 1/3 is -2. -2 cubed is -8. Minus 3 is -11. So sorry, right there. And now as we connect the dots, we got our nice function. So there it is. Boom, done. So this one is interesting, and this is what I usually recommend when trying to solve this. I would usually recommend trying to factor out that negative, and it's going to make more intuitive sense. You're going to see why in a second. So now we have it in this format, and I see that I've got a negation here happening to the input, which means this is a reflection across the y-axis. And then I've got shifted 4 to the right. So we're going to the right by 4 units. So now normally the square root function would be going like this, but it's now reflected and shifted to the right by 4. So we're going to start here, and then the next point will be here, and the next one will be here. And we're going to verify this in a second by plugging and chugging. So if you're unsure, right, I plugged in 3 and I said, hey, I think that's going to be 1 based on the transformation. Now plug it in. -3 plus 4 is 1. Square root of 1 is 1. Boom, done. Plug in 0. 0 plus 4 is 4. Square root of 4 is 2. Boom, done. And there you go. So for this one, we're meant to graph g of x, which is a negation of f of x shown here, aka a negative applied to the entire function. So what type of transformation is that? That is a reflection across the x-axis. So let me show you a quick way on how to apply this transformation. So first of all, anything on the x-axis is going to stay on the x-axis. Then what about this point? Right here, it's -5. Flipping it across, we'll go to +5. This one's at +5. On the y-axis, it's going to flip down to -5. And this one's going to flip up here as well. And we could do some other points. We could flip this one down here and this one down here. But we kind of get the idea. And now you can somewhat just basically connect the dots. You just want to kind of maintain the original shape like so. And there is your function. Boom, done. So for this one, we are subtracting 2 from the input. That is a shift to the right by 2. So what I'm going to do with every one of these points, or to a certain number of the points, is I'm going to move them 2 to the right. So this one here is going to go here. This point here is going to go here. This point here is going to go here. This point here is going to go here. And this point here is going to go here. So now we're going to connect the dots like so. And this is your sketch of g of x. Boom, done. I hope you guys enjoyed this video, and if you did, please click that like button. And if you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.